Let us go with the sinusoidal pulse width modulation, and this is 3-phase sinusoidal pulse width modulation, and we are going to run induction motor. So we need to design a sinusoidal pulse width modulation for that sine and triangular wave. Let's start from the scratch. Specialized power system, take the Power GUI. Then you have got let us take some source here, because the most important part is generating a triangular wave. So take a pulse generator, take another pulse generator, and what we're going to write here is this is the amplitude. Let us say 1 time period 20 milliseconds, 0.02 pulse width, 50% of the pulse width. This is what we see first, and here we will say amplitude, let it be like that, 0.02, pulse width 50, and the delay is 0.01, let us say half, right? So if you want to see these two together, we need a sink. Inside the sink we have a scope, and this scope we have put some design here. What is, we have to view configuration parameter. I want to see the 4 number. Okay, 3 at present, no, 4, let us say 4, and layout is like this. Apply, and the display, right here, all these things. Let's not write right now. Okay. We can view the style, and there we can make it color white, and this one is black. This one we can write, we can make it black also. First channel, display second, we can make it red. Let's make it black again. And the third one, where we want to get a triangular wave, let us make it red. And the fourth one, where we want to see our sine wave also, so let's make it blue. So this is our done. This is the output that we need to see, right? So now what we can here is, do we have here the scope? So what we will do is, we will just try to first see that what is our, these two we have connected to the scope, and just run for 0.1 seconds. We can change here, we can write simply like 0.1 seconds. We can have 5 cycles over here. So if we run like this, and I can see that here we have a 2 square wave, and 2 square wave, they are having a 0 to 1, another is 0 to 1, but there's a delay, right? Second one is delayed by half of the time. So if I will do like in second one, I will not give 1, rather I will give -1, and apply and run. So what I'm going to get here is, I'm getting the like negative, right? So it's like similar, but it's 0 to 1, and this is 0 to -1. So what I'm going to do is, when I add these two, if I add these two, I need to add a, okay, take it out here. If I add these two waveforms, and I see this waveform on the third, it gives us what? We are getting a square wave which varies between 1 and -1. We are getting a square wave. Now if I will do one thing more, I will integrate the square wave. Integration from that change in the level from -1 to 1, that is 2, divided by time during this. So 2 divided by t into t, integration will be t square by 2. So you can calculate that. And if I do an integration, I need an integrator which is available here, continuous, and I can take it the integration over here. And if I connect this integrator and want to see what is after integration, what I get here is this triangular wave, but this is from 10 to the power minus 3 from 0. It doesn't have any sense. So what to do? Okay, I want to make it like let us remove these two square waves. That's not required anymore, and we will start with this. We will keep it on the top, and then we will try to analyze that. Okay, so what I want to do, I will remove this. So let me keep one is a square wave, another is after integration, and then these two. What I want to do is, since my purpose is not resolved here, this is what a square wave, but this triangular wave is not from -1 to 1, so I need to change it to a value. This value will be 4 times of the frequency. Okay, before that, can I write this 0.02 as 1 by 50? And then if that is possible, can I write here also 1 by 50? And this is obviously 1 divided by 50 divided by 2. Apply, and we get it. What we get? Same thing we should get. Yeah, same thing. That's, everything is okay. So if I just make this amplitude as 4 times of 50. Okay. And here amplitude as -4 times of 50. Then let us see what I'm going to get. Oh, here we are getting something. What? We are getting it from 0 to 2 and 0 to 2, right? Still my purpose is not resolved. -1 to 1. What we will do, okay, we will use again an adder. Take it like this. One adder. This will be obviously a -1. Apply, and this one you can apply here. Now see what is the results. Okay, perfect. This red one is from -1 to 1, right? So this is we are getting a triangular wave. Let's see the sinusoidal wave at the bottom. So sinusoidal generator is there. So we have a sine wave. Here it is. So just we need to take this sine wave and connect it to here. Fill this sine wave. Amplitude is 1. Frequency in radian 2 star pi star 50. Phase. Okay, let it be like that. If I run now, what are we getting? Oh, we are getting a sine wave. This sinusoidal is not so perfect. So what we will do, we will take it continuous and just make it a discrete, and now run it. Still it is not coming, right? So here we have to write here 5e to the power -5. So that's the step size. So if we reduce the step size, simulation time may a little bit of increase, but we are getting a perfect sine wave over here. So now we can have sine and triangular wave done. And another thing, the frequency of the triangular wave should be 5 times or 7 times or 21 times or 31 times, like that. So how to do that? Let us say 5 times. Okay, so 5 times, what I will do, I will stop making 50, I will make it 250. here 50, I will make it 250. This 50 is pulse width, no changes. And here, instead of making 50, again I will make it 250. This is 250. This is 250. Done. Now if I run it, so I have got in one cycle 5 triangular wave, right? Yeah, now we get to zoom it up. In one cycle, you can see that in one sinusoidal wave, you have got 1, 2, 3, 4, 5. 5 triangular wave from 0 to 1 like that. -1 to 1, 1 to -1. We can show these two in a group, right? So, okay, anyways, we understand that this is all okay, fine. These are like generation of a triangular wave, and I just connected it here, so I can make this as a group, right? Right click and create subsystem. We can create a subsystem also, or we may not. Let us create subsystem. And what we are interested to see that we want to have a mask, so that the two waveforms we can see together here. So this one we can connect with the mask, this also with the mask, and this one we want to see any one of the scope. So what we will see, we see here a sine wave, and that, so let me make it this channel 2. We have got sine wave also, which is that is increase the thickness. Now we have sine wave and the triangular wave. The one cycle of the sine wave is having 5 cycle of the triangular wave. So in this way we can have both. So this is one. So ultimately our objective is to generate a triangular wave, sine wave, and then to have a SPWM inverter, right? So we have tested. This is no more required. So ultimately what we will do is that we have a sine and triangular wave. We keep this slope aside. Now we will make a inverter, 3-phase inverter. So what we need is a power alternate device. We can have a MOSFET. Where is a MOSFET? Is in IGBTs here. We can have a MOSFET. Let us take it out. This MOSFET we can control on. We will be giving a supply to the between drain and source. Okay, for that we used to just reverse it. Click on that one. Measurement that will give you the current and voltage across it. So we just need to remove that if I don't require it. So now this is a MOSFET, and if I give a DC supply over here, source, we take a DC supply and connect the DC supply over here, and we need a resistor also. So some resistor, series RLC branch. So this resistance only R. Value 10, this voltage is 100, fine, so we connect it here. So we need also to see the measurement of here. So what is the measurement we need to do? Here it is, ammeter and voltmeter. The other things are there, like a lot of things are there to play with, and we need to see what is the across that register. This is just we are testing one MOSFET, and this one we will connect here diameter, correct, and gate pulse is also required. So right now we will simply give a gate pulse to a pulse generator, which will give me just on and off. Time period 0.02, pulse width, let us say 50%. That's all. This one is connected with this. So we have a ammeter over here and voltmeter over here, and just because it is available, let us connect these things here. Okay, now if I run, what will happen? I have a positive connected to drain and negative connected to the minus. If I run, then what we're getting? So here what we're getting is the output voltage 0, 10, and this is the current, sorry, first one is the current, then we have a voltage. So we are getting it working perfectly fine, right? So if I'm connecting drain to the positive, and this is when the gate was not there, it is having the forward blocking mode. What we want to is a little bit of play with it. So let us say instead of having this connection, I will just do a reverse in the connection, like we are connecting to the source, and this drain part I will connect to the resistance. If this is the situation, how does this MOSFET will behave? Oh, this is, we are not getting anything or something. Oh, we are getting what? The output is always 100 volts. This is small drop, you can see neglect, and the output, the current is like fully on. You want to see that? Okay, let me see if I can do. Okay, configuration parameter, display. What I will do is that in channel 1, I will fix it from maximum while limit as 10 and the minimum, okay, minimum is 0 and maximum as 10. Okay, apply. And channel 2, we will fix it at minimum as 0, maximum as 100. Okay, 150. Apply. And first one is instead of 10, we will do 15. Apply. So what we're getting is this is complete, like 10 ampere is flowing. There is no effect of any switch. The MOSFET is not able to block the voltage if it is applied in the source side. So MOSFET can only block if the drain is connected to the source, not the drain is connected to the supply, positive. If source is connected to the positive, so MOSFET is behaving as a short circuit. Okay, so here, that's why we have tested that. So we need to remove these things. Let us remove, gate pulse is not required. Okay, we need to have this rheostat over here, not required right now. If required, we can bring it back. Voltmeter we need some time back. Ammeter also required sometimes. So this is supply voltage. We have a MOSFET over here. We can have another MOSFET. 1, 2, 3, 4. Pattern is familiar, right? For those who work with the inverter 5, 6. So this is the pattern we used to keep like this, but it's all the same. Here nothing we did it with the pattern. pattern will be required when we give us pulse here. So what we did, we joined these three in between. Positive we are giving to the drain, negative we connect to the source, and that's all. We just keep on connecting this positive with this and negative way here, and we can ready to give a load over this side. What load we are going to give? Machine, asynchronous machine, here it is. I need to give a torque, so for torque I need to have a constant. Here it is a constant, which is giving a 10 Newton meter, let us say. Next we have here sine and triangular wave, correct? I need to compare these two, compare it when sine is greater than, okay, let me keep it bottom. When sine is greater than the triangular, we can give a gate pulse here. Okay, where is a comparator? Relational operator. So I can have this one here and this one here. If this is greater than equal to, if I say greater than equal to or only greater, then if I is greater, I can give it a pulse to the topper one, and if it is control C, control V, and if it is lower, there are many ways we can have other options also, right? If it is lower here, in that case we will toggle the lower one, right? This is how it works. Other two, I'm just keeping it away. Okay, let me just keep it a little bit off here. If I take the same pattern from here, copy it. Let me remove it for a while. If I take the same pattern, copy it from here, and I give it here. 1, 2. This is, gives me 1, 2 over here. Another one. Okay, let me place it properly. This is not required. These things I will keep it like this. This one again copied and again keep it here. Easy, right? So we have all the three things here. So what the difference we make here, it is R phase, and this one I will just make a diversion over here. Phase is -2 star pi by 3, 120 degree, right? And the lower one will have +2 pi by 3. That's all. And now we can just connect it by control. This one and the lower one will do this. Similarly, the upper one with this, and the lower one with this. Upper one with this, and lower one with this. Our gate pulse is done, right? We need to give the supply to the load, induction motor load. Here also in the induction motor we need to connect a bus selector. Okay, join it. So here also we can connect it to a bus selector. This one we can connect. Okay, first we have to click it over here. We want to see mechanical speed. Remove this to. Then we see electromagnetic torque. Then we see stator current. Then we see rotor current. So we have 4 things there, and then we can just enlarge it. If you don't, no problem, and you can connect like this. Another thing is that we can make it sorted, or we can add a resistance. It depends. So for now, this is okay. Let me run it for nearly 4 seconds. let's see if we getting any results or not. Yes, we are getting some results. We're double clicking it. We are getting like it's decreasing, and so very weird kind of results. So what could be the reason? Oh, the voltage is very low. It is like, let's say 525. There is a reason, like we calculate that what is the value of VD, so that the line to line is 415 or 380 volts. Then you can divide by 0.62. In that way you can calculate. Then after doing it, we are getting still a current speed. This speed is not in radian per seconds, not in RPM, rather radian per seconds. We're getting some kind of torque here, with a lot of ripple. You can see that there's a lot of ripple over here. So anyway, what we want to do is we want to add some gain, that is 30 by pi. So if we remove this and you connect some value that will convert from radian per second to RPM. So this will give me the radian per second to RPM, and that will give the speed in RPM, right? So here we have the speed in RPM. We're taking up to 4 seconds, but we are getting a steady state after like 1 second, right? So need not to go up to 4 seconds. We can just keep it 1 second. It's done. Okay, let me make it. Okay, 1 second is enough, right? So what we want else to see extra? Okay, we can have this same scope. We can bring it here and see this one here. What we want to see. We need a mask. So there we need to see all the 3 sinusoidal wave, right, together. So 3 sinusoidal wave we want to see. So first one we connect with the R. Let it connect it gently with this R. Then we want to connect it with the Y. Then we connect with the B. Right, R by B we have connected, and this one we connect with. Right, our sinusoidal wave. Then we need to see the triangular wave. Okay, anyone triangular wave, and if we run, we can see the triangular and the sine wave together. Okay, if I connect a voltmeter over here, between line to line, I can measure the voltage. A and B, I can measure the voltage. Also, we can measure the current in our phase. We can measure this is giving. We can measure this R phase current here, and that voltage and current we can see it here. So this is all full. So now run. This will what we will get lot of data from here. So let's see what we are getting. If we double click over here, okay, we are getting something, right? What are these things? This is a 3-phase, right? R by B, and we have the triangular wave, and what you can see here is the line voltage. And here is the stator current, right? Stator current. Very wizard kind of thing. At steady state, if I see that this is the stator current, like this. So let me just keep it aside here. This is one scope results. And zoom it up. Yep. So let me just see the transient part here, and similarly let us double click over here and here we can see the speed and lot of other things. So what else we get here? So this is, oh, we have missed in this one thing. What? This is synchronous motor, right? The parameter is there, the slip we have didn't put it 1. That's why it is now initial value is not here. If now we run, okay, so now we get some values of RYB. If we click here, if we are getting the speed rising from 0 to this value, we get a rotor current, stator current, and electromagnetic torque. We are given a 10 Newton meter, the electromagnetic torque, but this gives me a very lot of ripple over here. So now you can see that if I'm using a SPWM technique, what kind of ripple I'm getting, and what is the voltage and other things we are getting at steady state. If you see the steady state, this is the case of steady state. This is the stator current, which is same as the current over here. Here in the steady state, right? So it's the same current. So induction motor stator current and this current, this will be nearly same. This is rotor current, stator current is this, and this is same. This is a torque, right? Sorry, this is the stator current and stator current over here. This is a torque, and torque is supposed to be 10 Newton meter, but it's like a lot of ripple. Rotor current is like this, and we have a speed a little bit lesser than the 1500, obviously. So now what we can do is that in the triangular wave, instead of having the 250, we can write, so like 250 is 5 times of 50, right? So if I say 10 times, it is 500, 21 times. So if I say 21 times of 50, so that will be coming around 1050, right? So let me make it frequency as 1050. So these things I will copy and I will keep it everywhere like this. So we are going to add this 1050 everywhere. So if I'm adding this 1050, so what I will do is that, like, let me just copy these two things over here, and when I do make this change over here, I remove these two and I join these two from there to here, right? Done. And this subsystem also, I will remove this, Control V. So what I can do is I can join these two here. Done. Right. I need to change, modify everywhere. So now when the switching frequency is very high, like it's very high, right? 21. How does the speed torque characteristics look like? Now if I run it, oh, now you can see that this ripple has reduced a lot, right? Rotor current gets smooth, and stator current, you can see that smoothen up. Torque ripple decreases a lot. You can see the differences, like in previous you have got a like minus between oscillating a lot. Now it is from 0 to 20 only. That's the situation. And see that output here, you can see the sinusoidal, and triangular is like so close, it's very difficult to get it all these values. And these pulses are, you can see earlier you have got very less. Now these pulses are a lot of pulses are there. This is the line voltage, so you can see the line voltage look like this. This is the line voltage at steady state, right? At steady state, the line voltage look like this. So one can take that print out of that with the taking a file, and you can take a print to figure and other things. In this way, the simulation of sinusoidal pulse width modulation, driving an induction motor, squirrel cage induction motor, and you can see that output voltage, output speed, torque, and rotor current, stator current, and all these things you can see that. So that's all. Thank you everyone. Take care.